Okay, so our first speaker in this session is Professor Jane Ashby from Central Michigan University, and we will have one further talk by Professor Mal Joshi afterwards. From one extreme to the other, from preschool all the way to skilled reading. All right, so this will be a change of pace for you. So in my dissertation work, I did eye tracking and EEG at UMass, and so what I do is I look very, 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 very closely at a very, very small span of time and try to figure out what is going on with the cognitive processing. All right. And I'm trying to leave my cognitive psychologist self behind, and I will not flood you with data, but we will see a little bit, and you'll get a nice exposure to sort of what the paradigms are that we use. So my topic today is prosodic processing and how that supports skilled reading. I think most of us think of prosodic processing and prosody as being intonation and rate during reading aloud. Right, or speaking, maybe we think of it in terms of inner speech. I'm looking at prosodic processing at the lexical level. All right, so I think that the lexical level prosodic representation perhaps sets the foundation for the sentence level metrical representations that are more in line with what we think of typically as prosody. And these are referred to as prosodic representations because they're suprasegmental. So it's phonological processing above the level of the phoneme. Okay? So that should be a nice orientation. All right. So when I started graduate school, which was quite a while ago, my question was, why do children with a phonological deficit have slow reading? So I worked doing reading remediation, and I remediated several children. I supervised other teachers, and even in English, when they can decode fairly well, they remain quite slow. But I went to work in a lab where they didn't work with dyslexic children, so I had to kind of flip that question around. And so my question became, what is the connection between skilled phonological processing and reading fluency? So what are skilled fluent readers doing with their phonological processing that is enabling them to read quickly and smoothly? Now, the typical view of reading development is that we have unskilled reading, which is kind of decoding, it's slow, it's effortful, it's phonologically based. And then children get better and faster, and they become skilled readers, and they have direct access. The processing is mainly orthographic and morphological, right? And this is not a view of reading that I espouse. And I think some of the confusion comes from the way that we think about the term phonological processing. So, of course, there's several types of phonological processing, and it changes with development. Okay? So initially, phonological decoding, which is going to be serial and slow and laborious, and we all know what that sounds like in early readers. Then phonological recoding, where they become faster, right, but it's still serial. So my question is, what does skilled automatic phonological processing look like? And how does that contribute to reading fluency? Now, of course, as Johanna referred to, there are a pile of homophone and pseudo-homophone studies with lexical decision and naming and masking and backward masking, and they all indicate, of course, that phonology is involved in skilled reading. But we kind of stopped asking the question at that point, and I wanted to take it a little bit further. I wanted to know what is the nature of phonological processing, what is the time course of it, and what I am going to assert today, I'll give away sort of the take-home at the end, that I think skilled parafobial phonological processing is actually a gatekeeper of reading fluency. And this is going to be a bit of a controversial talk. All right, so the three main questions, and I have three sections of the talk. One talks about each of these issues. So let's turn to what is the nature of phonological processing. So phonological processing in speech, we know, has multiple layers of information. So there is a feature subphonemic level, then there is a phonemic level, a skeletal level, a syllable level, a prosodic level, and the level of lexical stress. And linguists have quite a bit of evidence for these multi-layered representations that seem to be hierarchically organized. But all the research in phonology and reading has shown, up till recently, is that the phonemic level is what is operating. That's what you're seeing being represented with pseudo-homophone studies, etc. Right? So my question was, what is happening with these other layers? Are skilled readers representing these other layers of phonological information? And so I use two online measures. I like to use eye tracking because it allows an unobtrusive measure of silent reading, right? And you get reading fluency as it naturally occurs during text reading. And by the way, you also get word recognition the way that it naturally occurs during text reading, which means that it starts paraphobially and then it completes while the word is being fixated. And you can't get that information from single word reading studies. Then after a series of eye movement experiments, I decided to get involved in EEG because, as you all know, EEG gives you a nice high-resolution picture of the time course as word recognition unfolds. So you can see very clearly what information is being processed when. Not where, but when. Okay, so I just put this up here as an introduction. So where the text is clear, that would typically be the fixation point, and then the area surrounding the text becomes progressively less clear, and readers are only able to pick up a tiny bit of information to the right and left of fixation. So we're using eye tracking as a dependent measure, and it's a very sensitive dependent measure, so it's sensitive to reading ability, word frequency, predictability, semantic ambiguity, etc. All of these higher level linguistic processes seem to affect fixation durations on words. All right, so as I mentioned, when reading text, skilled readers begin word recognition before they actually look at the word. So here's an example, sort of perceptual span. This shows a symmetrical perceptual span. It's sort of evenly fuzzy on either side, but real perceptual spans are not like that. They are asymmetrical. So it would look more like this circle here, where when you're reading English, you would get information about the word that you're fixating, and then a certain number of letters and words to the right. And that certain amount of numbers of letters or words to the right is not processed consciously, but that is what we call the paraphobial view. All right, so we know the brain is picking up that information even though readers are not aware of it. The perceptual span for spacing of words is much longer than the perceptual span for actual letter information. So that inside dark green circle just indicates that you're usually picking up information paraphobially about just the next word that you're going to be processing. Okay, it's not like you're paraphobially picking up words that are 2 or 3 words ahead. It's usually just the next word that you're processing. Interestingly enough, this seemingly visual construct is orthography specific. So for readers of English, the perceptual span is asymmetrical, moving towards the right. For readers of Hebrew, it is asymmetrical, going towards the left. Okay, so the paraphobia preview is always going in the direction of the upcoming text that's about to be processed. Also, the span increases with reading development. Right, so we see a pretty steep increase in span in 2nd and 3rd grade, a little bit more until about 5th grade, and then their reading spans are about similar to those of skilled readers. So this paraphobial information that is processed automatically by skilled readers without their conscious awareness, it is involved in initial lexical access. It makes word identification about 30% faster. So skilled readers are a third faster when that information is available than when it is not available to them. Paraphobial information is only available during text reading, not during single word studies. All right, so that's a little bit of general background. Then the last background piece I wanted to show you was just an example of how my further examples are going to be set up. So here we have a sentence. The asterisks above the sentence are fixation points, right? And this is just indicating that when they are looking at the word process, okay, they are getting paraphobial information of the word text. If that is a high frequency word or a highly predictable word, they may process it without looking at it, just process it paraphobially and fixate the word following it. Okay? But even if they do fixate the word text, there will be some advanced information that they have processed about the word form. All right, so here's an example of what readers see. So the first thing they see is a fixation cross on the far left-hand side of the screen. So that draws their eyes to the beginning of the sentence. And then after, it's a gaze contingent display, so after they look there for a while, the sentence comes up and they read silently, Jim carried the rusty. And while they are on rusty, they are getting a particular preview of the next word. Okay? So that little red boundary there is the invisible boundary that controls the display change. So what we are doing is we're manipulating the text that readers see and when they see it. So they're looking at rusty. As their eye moves to go towards the next word, the word changes before they land on the word, and they see lantern inside the tent. Okay. Now, as odd and strange as this may seem, when you are sitting in this experiment, I can't actually tell whether it is working or not, because I cannot see the changes in the text. It's that good. I mean, the participants are mostly completely unaware of what is going on here with the text change. So that's a paraphobial preview technique. That's the type of manipulation that I'm going to show you in the experiments that are coming up. All right. So as I said, we already have plenty of studies in reading that show that at the segment level, there's phonological processing by skilled readers. So I thought, well, okay, what happens if I look at the onset rhyme level? Right, and truth be told, this was not my idea, it was Becky Treeman's idea, but, you know, so, okay. So we're going to look at the onset rhyme level. So this is the word candy, okay, and we have the phoneme segments at the bottom. And then the rhyme is simply the vowel plus the following consonant in a syllable, all right? Now, why would skilled readers process onset rhyme information? Well, Becky Treeman's work has shown that they do it in order to reduce vowel ambiguity in English, all right? So as you know, English is a freak orthography. I love that phrase. And so here are some examples. The letter A can either sound like it does in stall or in staff. Okay? OO can sound like in took or like in tool. And what Becky Treeman and Brett Kessler have found through their corpus analyses, in addition to other experiments, is that readers implicitly develop sensitivities to these letter co-occurrence frequencies that allow them to predict vowel sounds. So what does that mean? What it means is that when, as in stall, when A is followed by LL, you never have to guess what the sound is going to be. It's actually consistent, very consistent. And there are several of these rhyme patterns that are consistent in that fashion, and it turns out as reading develops, children develop sensitivities to these rhyme patterns, and it allows them to preferentially activate a certain type of vowel sound. So here's an example. And in this experiment, I'm going to go through it a bit slowly, and then when we get to the syllable experiments, it'll all be familiar, and I'll go a little bit more quickly, but just to make sure everybody's on the same page. All right, so here's the sentence, and here I have the target word italicized, but of course it doesn't appear in italics when people are reading it. And they see a preview that is a non-word. It's either druk or it's droon. Right? And druk is pronounced druk because the K follows the OO, so again, that is the sensitivity to the rhyme unit. Okay. So in the vowel different condition, they're reading along the sentence, and when they're looking at sweet, they will see a preview that is something like snall. Right? When they cross the invisible boundary, it will turn to snack, and then they continue reading. So as in my previous example, the sentences appear in one location on the screen, so the change is not visible. In the vowel same preview condition, the rhyme information is consistent with the target. So it's very simple. Are they faster to process the target when it's preceded by one type of rhyme than the other? And indeed they are. They are faster to process targets that are preceded by vowel congruent rhymes than vowel incongruent rhymes. So that's evidence for paraphobial processing during silent reading of, just file this away, information that isn't explicit in the text. Okay, we're going to come back to that. Well, that was fun. So now let's look at syllable processing and see what we can find there. So again, I'll go through this design kind of slowly. This is a similar design to what's used in the EEG studies, so just to make sure everybody's clear. So we had two types of target words embedded in sentences, words that start with a consonant vowel syllable, like magic, and words that start with a consonant vowel consonant syllable, like magnet. And we preceded those target words with different types of previews. So for the words like magic, the incongruent preview had 3 letters, and the congruent preview had 2. For the CVC words like magnet, the incongruent preview had 2 letters, and the congruent had 3. So you see here we're controlling for the amount of orthographic information and manipulating whether the phonological information is congruent or not. Now, I've done several of these studies, and in some of them, there's no information after the syllable, okay? In some of them, there is a unpronounceable letter string, like ZX, Z, okay? In some of them, there's Greek characters. It doesn't actually seem to matter, okay? So here's an example before the boundary change in the congruent condition. When they're on powerful, they're getting a paraphobial preview of magic, which is congruent, right? And then when they cross the boundary, the word appears and they continue reading. In the incongruent condition, okay, they get the same preview, okay, only this time it's incongruent because it's a preview for the word magnet. and the words, the CV and CVC targets, are embedded in very similar sentence frames, okay, at least before the target, to control for that. All right, well, I wouldn't be here talking about it if we didn't find something. So what we found was that skilled readers are faster to read the word magic when it's preceded by a congruent prime, MA, than an incongruent prime, even though the incongruent prime gives them one more letter of information. Okay. Now again, this is information that is not actually in the text, right? It's not, we don't separate our words by syllables like they do in the Chinese writing system, right? So this is information that is not delivered actually by the text, although there might be implicit learning of some co-occurrence frequencies that contribute to syllable sensitivity. But this is a very strange finding in English, because English is known for being having very fuzzy syllable boundaries, and the syllable is also not particularly salient in English because it's stress timed rather than syllable timed. Don't worry about what that means, but it's not particularly salient. Yet we find these syllable congruency effects. All right, so that's a little bit about the nature of the phonological representations that skilled readers form during silent reading. It looks like they represent rhyme information. There's also evidence for syllable representation, and other experiments give evidence for lexical stress representation. So now let's look at the EEG studies that talk about the time course. Okay? Take a look at that. And I'm going to show you two studies, one of which is Prosodic, which is the suprasegmental syllable information, but there's also evidence for subsegmental feature information processing. And I mainly put that in the talk for Ken. All right, so the EEG experiments, some people do co-registration with EEG and eye movements, but I'm not smart enough to do that. So I just do straight EEG and don't let the eye movements interfere with the brainwave. So we do RSVP presentation, and we use a mask priming paradigm. So I wanted you to see what that is like. Okay. Okay. So maybe what you saw was a fixation cross, then some number signs, and then the word. Well, that's what you think you saw. But what you actually saw was this sequence. Okay? So it's mask priming. So we present the fixation cross, the forward mask, then a non-word prime, very briefly for under 50 milliseconds, followed by a backward mask, followed by the target. So again, readers are not aware of the phonological or orthographic information they're getting in the prime, right? And we're looking at how their brainwaves respond to the target in the two different conditions. All right, so let's talk about the feature, this subsegmental information experiments first. So there were, these are all set up the same way. There were two studies using the same materials, using different participants, and all we did was vary the duration of the backward mask, the mask between the prime and the target. So we had voiced targets where the last sound is voiced in English. So we have fad versus unvoiced, fat. So the idea is the other articulatory information for that last phoneme is similar, but the voicing is what distinguishes the two. So these are all minimal pairs. So for previews, they saw non-words that were either congruent or incongruent in terms of how they matched the feature information of that last letter, okay, that last phoneme. So for fad, it would either be preceded by fac or faz. So faz has the voiced last phoneme, so that would be considered congruent with fad. Okay. And again, we had them matched so that we could do this nice, complete orthographic control. All right, And again, this is just an example. This was just a prompt for me to tell you that we did 2 different studies varying the time of the mask. Okay, it came out a little bit better than I thought it would. All right, it's still not terribly clear. We found feature congruency effects in several time windows that are in yellow down here at the bottom of the slide. Experiment 1 had the long mask time, and experiment 2 had the short mask time. And so what we see is, in both experiments, we see feature congruency effects right around 150, 80 to 150 milliseconds, depending on the duration of the mask in between. So these are quite early effects, right? We heard a talk yesterday, probably more than one, talking about, some of you are familiar with the N170, right, which is a very early component of orthographic processing. Okay, so this was quite a surprise. And that's just a designation of how we would think of early, middle, and late effects. All right, so then we did another study with 2 syllable experiments. Again, different set of materials, but quite similar, matched for initial trigram. Same design, only now we're doing mass priming. Okay, and so this is our paradigm, and this time the syllable information actually had symbols after it in the string. It wasn't just an underline or an empty space, and this was to reduce the visibility of the prime. And up at the top there, the sites in black are the electrodes that we analyzed. So in experiment 1, these are the midline electrodes right here that you see. And basically what you can see is that on the N1, which is earlier in this paradigm than 170, but on the N1, you can see that there is clearly an increased negativity to the incongruent condition than the congruent condition. So the incongruent condition is going to be the dotted line, and following tradition, negativity is plotted upward, right? So it's an increased incongruent negativity in the incongruent condition. And this was bilateral and pretty much across all the electrodes. All right, in the study where we used a 22 millisecond backward mask, so a shorter backward mask, what happened, sort of to our surprise, is the N1 seems to be pushed ahead in time. And so it is more right around, that 80 to 120 mark. And again, you see increased negativity in the incongruent condition. Now, if we hadn't had the eye movement studies, we wouldn't know what that increased negativity means. But we do have the eye movement studies. So in the eye movement studies, we saw longer reading time in the incongruent condition. And in the EEG studies, we see increased negativity. And that is pretty consistent with the interpretation of increased negative amplitudes in EEG, that it's more effortful processing. So I thought I would spare you and not show you all of the studies that have been done, and these are just the ones I've done in English, but there are others, of course, in other languages, in Spanish and French and German. But these are some of the papers. And what all these papers have in common is they all indicate that skilled readers are processing phonological information that is not actually in the text. So it can be derived from the text, but it's not in the visual signal. How can that be? That is so strange. All right. So here we get to the controversial part. All right, so let's talk a little bit about what all these studies together tell us. All right, there are some. So one is that we know that skilled readers process phonological feature information extremely quickly within the first 100 milliseconds. This is actually earlier than the orthographic effects that have been found. It doesn't mean that phonology is processed earlier than orthography. It just means with the present paradigms, we haven't been able to find orthographic effects in this time range that I know of anyway. All right, so just to give you a feel for this, I hope this works. We'll see. Now this is PowerPoint time, okay? But that's a second in PowerPoint time. All right, now here's what 100 milliseconds is. Okay, that's fast. It's real fast. So just when I was about to not even believe my data, fortunately some papers have come out that have found early activation in the IFG. These are MEG studies. And it was very fun. I was at SSR actually when Pierce presented this last study. That was a good time. So there are these MEG studies that are finding very early activation in the IFG. These studies are single word reading studies. They use pseudo-homophones, right? So the alignment is not perfect, but I was comforted. All right, so we have these different methods, at least 3, that converge on some conclusions about phonological processing. All right? So one is that I can't count, because there's 4 conclusions, not 3. But clearly, phonological processing of skilled readers is not slow. It is not minimal. It is not some kind of phonological sketch that we later fill in with information we retrieve from memory. Okay? And it is not redundant with the orthographic information that's on the page. Well, if that's the case, then it can't be a deterministic representation. It can't be a solid representation of like, this is what the phonological form is, right? It has to be a probabilistic representation, right? So somehow readers are forming these prosodic representations probabilistically. They're probably updated continually during the word recognition process as they get more information. So because of the previous conclusions, we really need a new story about phonological processing in reading. We haven't had much of a story since 1998, so it's time, and we really need a new story. So here's my story, okay? And I'm very happy to be able to share this with this small, friendly group. But I encourage your challenging comments as well. It's not a complete story. It's not an ironclad story. It's the beginning of a story. So let's talk about how readers might process phonological information that is not explicitly encoded in the text. All right? And in that, we'll also talk about the function of those representations. All right, so as I said, the first part of my story is that we have these very quick activations that are probabilistic and flexible. Okay? So representations are probabilistic and flexible, which means if new information comes in and the reader finds out that it's wrong, there's going to be some revising of the representation. Especially in opaque languages, orthography is like English, the representation is necessarily going to be partial. Okay. So minimality claimed that there were mainly phoneme segments represented. What I'm saying when I talk about partial, I mean that there are going to be multiple layers of phonological information, but that those layers might not be complete. Okay? And what affects the completeness of the representation are things like reading skill, orthographic transparency, how informative the letter string is. Okay? All of that will affect the degree to which readers will be able to form these probabilistic representations. Okay, it was getting late when I was at this part of the talk. So I thought I would write down just so I remember what to say here. Let's see. Okay, so there's the controversial part. That by probabilistically representing phonological information, I think that early activation in the IFG could be activating production codes, okay, that are part of this probabilistic activation, and that when skilled readers do that, they actually generate an additional stream of information that constrains the information they get from the letter stream, okay, especially in English. All right, and we're going to go through this with rhyme information and make it a little bit more clear, okay? So the idea is that this skilled, fast, phonological, prosodic representation is used to constrain the set of possible lexical candidates that are being activated by the letter string. And so that would indicate a feedback effect from IFG to the visual word form area. Okay, good. Nobody's yelling yet. Okay, great. All right, so let's take the example of the rhyme units. So we know that in English, when they see that letter A, they could be activating two possible vowel sounds. So if you think about the group of possible lexical entries, there's a whole group that has that ah sound. Then there's another group that has, that has the A. It is all the words in English that have the letter A in them. Okay? But if you have that prosodic information, you can automatically rule out half of those words. Okay? And you don't have to have competition between those candidates. And I think that's what makes the skilled readers faster. And this didn't really come together for me until I ran across a recent paper that Kathy Price is on called Reading Front to Back, which is in Cortex. And then I went back and found that they had actually proposed this. They had proposed automatic top-down activation in IFG, modulates the activity that we see in the visual word form area. But what they didn't have was, they didn't really understand what advantage that would give over the letter string alone, right? Nor did they have any information about the behavioral result of having or not having that feedback information. So, in a nutshell, automatic probabilistic prosodic representation supports reading fluency by speeding word recognition. Okay. By biasing vowel activation, which reduces the phonological ambiguity in the letter string, particularly in non-transparent orthographies. Also by providing an additional signal that constrains orthographic activation. And I put Harman Seidenberg up there because this is an interesting paper. In this paper, they found that their model performed better even reading irregular words when it had phonological input. And this story kind of fits with that finding. And it also specifies and stores phoneme sequence information. Right? So in Jonathan Granger's recent paper in Cognition, where he's talking about orthographic processing and how that supports word recognition, he basically proposes two sort of rough orthographic coding and then a fine orthographic coding system that is going on. And that may very well be true, but it's not really necessary because once you have the prosodic information, you have the phoneme sequences stored and represented. So far, I haven't been able to find evidence that is inconsistent with my story. But I'm hoping I'll hear some afterwards. So there we are. So linguistic information that is not visible in the orthographic code makes reading faster for skilled readers. And that is all I have. So we know that these complex phonological representations are generated for multiple purposes, right? So when we're thinking about fluency and fluency intervention, okay, when you're teaching phonics, you're strengthening neural networks that contribute to skilled reading in several ways, okay? Not just one way, in several ways. So decoding, recoding, but also automatic phonological processing, and being able to generate those expectancies that are going to speed word recognition. So, thank you.
Thank you very much. We have time for some questions.
And, and while I'm taking comments, I just wanted to put this up, which is from the Price and Devlin paper, and it's just sort of a visual sketch of how that feedback might actually work. Yeah.
So, beautiful presentation, and as I think I told you, we've sort of come to the same conclusion, happily at one level, because it suggests a role for the gesture, for the speech gesture, in early, and extremely early, constraint on word recognition. And of course, Haskins people kind of like that role of the motor system. But it's also, we were involved in the Weed et al. Papers, that's Steve Frost on that, and we were blown away, as everyone else, at finding that early IFG. And there is other evidence that suggests this privileged link between ventral visual and IFG. So even in the Vinkier paper, where they showed progressive abstraction for more linguistic-y stimuli along that plane, they found a parallel in IFG that was medial to lateral and didn't know what to do with it. Basically, they just said it's there.
Yeah.
But given the Weed et al. Finding of this early phonologically tuned IFG that's coactive with visual cortex, I think the story really comes together. Two things that I'm actually adding a little bit to the story. So one is, this is of course the problem with hemodynamic imaging. You don't know if you're looking at a feed forward or a feedback effect, and it shows the need, students in particular, for multimodal imaging if you're going to do psycholinguistic theory, where it's the timing and not just the location that matters. And there are a couple of findings that really reinforce this in a slightly different way. We've published stuff where we looked at lexical decision versus naming. And if the VWFA were simply a feed-forward system, the way it was envisioned in DeHaan's idea, there should be no difference between naming, which is say the word, or lexical decision, which is discriminate words and non-words. But you see increases. There's also Bruce McCandless's stuff on the N170 and the interaction between STG and the so-called word form area, suggesting it's kind of an expert system that coordinates and organizes. It's still crucial for skill, but it may not be simply a feed-forward system. And then the last piece of evidence that I think it points to the role of the speech gesture in sublexical phonology, you can look across many phenomena. We did a study years ago on skill development, Cates et al. 2005, where we simply repeated stimuli. And what you find is, in lexical decision naming, what you find is you can predict how much IFG, how much mapping into that space you'll see as a function of whether the task continues to demand speech and whether the items are repeated in a silent reading test. Then IFG goes away. And even developing readers, the more you develop automaticity, the less you map into that space, and the smaller the regularity and other kinds of gesture-related effects are. So I think there's a big line of evidence. This is why I'm so excited and rambling. There's a big line of evidence suggesting this rethink that you're putting forward that really goes in many ways to people looking at reading development, because it suggests the importance of making the links not just to perception or metaphonology, but actually to the quality of perception-action dynamics. And I think it's a beautiful story. So I just wanted to add all of that. In a sense, I'm throwing it in, but I hope it's relevant.
All right, thank you for that question.
Yeah, was it?
All right, so I'll just say a couple things in response to that. So clearly we know that the VWFA activation starts increasing pretty late in reading development, right? So in Daniel Brandeis's talk, he talked about the tuning of that, and what a better way to tune that area than having feedback information as well. But I would differ with the interpretation that the more skilled your reading is, the less IFG activation you're going to get. If I understood you correctly, I think it has a lot to do with the activation appears to decrease depending on the paradigm. Skilled readers don't like to perceive their phonological information consciously, right? That's one of the consistent points with my research, is it's got to be masked, or you start getting conflict with the orthographic information, and of course the orthographic information is going to win. But in real reading, the phonological information that's available parafobially is not available consciously, and that's how it's able to still continue to operate in silent reading for college-level readers.
So the critical experiment to adjudicate this notion is, for example, to take the MEG effects of the Cornelison group and simply embed it in a repetition or a naturalistic reading context. And one prediction would be, if you can reduce that specific modulation of IFG at what is it, 150, to phonological priming, if you reduce that with repetition, that goes to the argument that it's flexible and in a sense, expertise dependent. But if you're right, and you probably are, it will be present no matter what, and it will always be present in naturalistic reading.
Yeah, except that I would argue that you need to use masked priming. Yeah, you need to use masked priming to bring it in again under the so it's not only implicit, it's you know what I mean? It's like one step more removed. If you just have a repetition task, you might not see that, but we can talk more about that. We can talk more about that later.
We actually have to continue, but I'm glad we'll all have some interesting conversations over lunch. So thank you very much.
Okay, good. Thank you.